working. No?
I mean, you can do the first one.
Okay. 0 to 3. Name. I say 5 plus 9 pi over 4. You agree with 5 plus 9 pi over 4 is the first? All right. Okay, now the question is, did I get you with the second? Yes, you just know already that I got you. For f at 6, did you build off of f at 3, or did you go start from scratch back to f at 0? Either one's fine, I don't care, but... Alright, let's go with that. Although that's going to involve redoing some work I already did. That's okay. Rearrange. F at 6 is starting point plus change. Did I do a mistake? Okay. So 5 plus 9 pi over 4. Here's common mistake land. The region from 3 to 6. What'd you get for that area? Okay, so what's the base? 3. What's the height? Ah, see, I got you. The height's not 3, it's negative 3. Those are negative y values. So that's a negative 9 halves for that area. It's area below the curve. So negative 9 halves. If you were to combine that, then that's 10 halves minus 9 halves. It's something like 1 half plus 9 pi over 4. Cool? Negative y values make for a negative area calculation. All right, and then f at negative 3 involves a little of the going backwards. I strongly, I beg you, please go least x value to greatest x value. So I want to get f of negative 3 in here, and I want to use f at 0 because that's what I'm given. Negative 3 comes first. By fundamental theorem, that's f at 0 minus f at negative 3. So if I want f at negative 3, I need to move it over here and this guy back. And so f at negative 3 is actually f at 0 minus the area under the curve. Think of it as undoing the change. All right? F at 0 is 5 minus 9 pi over 4, right? Okay. Last but not least, just for going for gold, talking about making sense of all this. Wouldn't you agree that if this is f prime, then it communicates to when the function is increasing or decreasing, right? Okay, now I know that f was 0, f was 5 at x equals 0, right? Don't worry about where that dropped in the front. But wouldn't you agree that the derivative was positive in this region? So f must have increased. F prime is positive. So f must have been increasing. Well, doesn't it make sense then that if I go backwards, f at negative 3 would be less than where it was at f at 0? You with me? If it increased from here to there, then here it must be less than at that point. And so it makes sense that it's 5 minus. Okay. All right, that's it. Let's go on to motion, shall we? Motion part 3 of a billion. Velocity, some of this is review, some of this is new. Stick with me until we get to something that interests you, although hopefully it all interests you. So, would you please, I beg you, recall velocity is change in position with time. So in physics, in junior physics, you talk about velocity as the change in position, change in position over time, yeah? But that's over a time interval. In calculus, we talk about change at an instant, and so that is not delta x, but dx. Tiny changes in position over the tiniest time frame. That then is velocity at an instant? Velocity at an instant is the derivative of the position. Now, sometimes you call position x. In fact, you crazy physics people always calling it x. That's crazy. Even when it's moving up and down, it's called x. That's what it is. Big over there. But anyway, s prime or y prime, yeah? Acceleration is the second derivative. Now that makes sense because acceleration is change in velocity. If acceleration is change in velocity over time, then if we had a time interval, it would be delta v over delta t, a time interval. But at an instant, acceleration is an instantaneous, microscopically small change from one point to another. That is the idea of the derivative. The tiniest little change interval, dv over dt, or if you like, v prime. Now, because acceleration is the derivative of the velocity, and velocity is the derivative of position, we could also say that acceleration is the second derivative of position, right? So, let's see. Don't look at your notes here. Heidi, what is acceleration the derivative of? Sorry. Go ahead. Derivative of velocity, perfect. So, yeah, I just haven't struggles. What about, what's it, the second derivative of, Esther? Acceleration is the second derivative of position. Well done. What is the relationship of position to velocity, Chance? Actually, you can give me two different answers. Give me one. Oh, that's true. Actually, give me three different answers. What about derivatives? Position and velocity relationship. Karis. Larissa, give me a velocity position relationship in calculus. Velocity is the derivative of position, or how else could you? That's true. Position is the antiderivative of velocity. All right. Sorry to call on you in my class. All right. Given position function is this ugly function. Find the velocity, no calculator, and acceleration at time equal 2. Now, this velocity should be easy enough if you use the product rule. So would you take the velocity derivative first, and then we'll talk acceleration. And I need to get out my calculator. Oops, FERPA. Okay, so v equals x prime. You should always write the calculus relationship to communicate. Velocity is the derivative of a position. First is the same, derivative of the second. Plus second is the same, derivative of the first. Okay, do you agree with my derivative? 2t squared times 1 over t plus 1 plus log of t plus 1 times 4t. Product rule, product rule, product rule. Okay, at 2 then, we would get something like 8 over 3 plus log of 3 times 12. Say your multiple choice answer isn't there. What's another way to write log of 12, log of 3 times 12? What's another way that can be written with log rules? It often is. Erica, how else could you write log of 3 times 12? Or actually, I'll write it this way, 12 log of 3. How could that be written? Do I have an error? Oh, because you're saying it should be 8. My bad. Never mind. Take it back. There's no 12 in there. It's 8. Now, Erica, how else could this be written via log rules? 3 to the 8th, yes. That often happens, multiple choice, they often play with the log answers. And so keep that in mind. Now, go to your calculator, please. Let's say we wanted to put this into the calculator. I want you to see two ways. One for people with confidence in their calculus, one for people that have zero confidence in their calculus. Goes like this. There are two ways to get the derivative in your calculator in the home screen. What's one? What's one? Menu, calculus. What's a blue? What's a blue pen? It's not letting me. Anybody see my blue? Oh, here it is. Okay. Oh, come on. I'm getting a real arm workout here. All right, here we go. So you said menu calculus, and that's true. That is the way I first taught you to do it. Did you also know that it's in here? In this little catalog of functions? It's right there. That's nice too. Derivative with respect to x of. Now, of that function, we got, now, do you agree that we could put in our derivative to get the second derivative? We got velocity. Now, acceleration at 2 is v prime at 2. And I said you can have your calculator do that, right? So I could take the derivative. I'm using x here. Could I just mentally change everything to x, or do we have to use t, or could I use x? I could use x if I make everything x. You can use t if you like, whatever you like. 2, so I need 2. That's a lot to put in. 2x squared times, or divided by, check that, divided by parentheses x plus 1. Are you with me so far? Are you having a lovely day? Geez, you can't even answer that question. You stink. Log of x plus 1 times 4x. Boom. Oh, shucks. Now, if you do it this way, you have to give an evaluation bar. Do you know how to get an evaluation bar? It's right here. It's in this little equals submenu. It's really nice. Evaluate that at x equal 2. You follow? I get 8.8388. How about you? We?
I got it.
You did not get that? Can I get a uh-huh? I heard a no. I heard some uh-huhs, maybe. Okay. Did you know that if you are a real sissy, that you could actually have the calculator do the derivative twice? So you could say, do the derivative with respect to x of the derivative with respect to x of the original function, which was 2x squared times, just in case, the log of x plus 1. What's going on here? Go over here. Evaluation bar. Nope. Evaluation bar. Boom. At x equal 2. I hope this works. Oh, no me gusta. What happened? Why didn't that work? Oh, maybe you can't do that then. Pretty sure you can. I'll have to play with that. Never mind. We'll just go with the first way. All right. We have a lot to do. I'm going too slow. Here we go. Would you talk to me about how I could take this position function and find when the car is moving right? You would start by making a calculus connection. Moving right implies what? Velocity is positive. And accelerating. Our book uses acceleration versus deceleration. Accelerating in our book, therefore, implies acceleration is positive. by making a table of velocity and acceleration signs. So, let's talk about this. Can you give me the velocity, please, which is the first derivative? 3t squared minus 12t plus 9, 3t squared minus 4t plus 3. How does it factor? Take 3 out, and it's t minus 3, t minus 1, right? Okay, so it's momentarily at rest or not moving at times 1 and 3. I'll use that in a minute. Sorry, t equal 1 and 3 are critical numbers for the first derivative. Now let's talk acceleration. Is the first derivative of velocity or second derivative of position? What is the second derivative? 6t minus 12. Do you agree that this would change signs at 2? Now, let's make a supercharted movement, shall we? Let's start with a time interval from 0 to our first interesting point, which is 1. Okay? Then we're going to go from 1 to our next interesting point, which is 2. And then from 2 to 3, and 3 to infinity. Now we're going to analyze both velocity and an acceleration. Are you with me? Okay, so let's talk velocity. Wouldn't you say that if it's a parabola E shape, x squared, then it would probably be positive, negative, positive? We could sign test that a little more, but it's positive before 1, negative from 1 to 2, still negative from 2 to 3, and positive after 3, yeah? Acceleration, when is it positive and negative? It's negative before 2 and positive after 2. Now answering the question, when is the car moving right and accelerating? Moving right would mean velocity is positive, accelerating means acceleration is positive, when are both positive? 3 to infinity, okay? V and acceleration are both greater than 0 on 3 to infinity. Later on, we'll talk about speed. Did you guys talk about speed, Cal Connors people last year? Yeah. Okay, when is speed increasing? What is the absolute value of velocity? Speed is increasing when velocity and acceleration have the same sign. So you would say there and there. We'll talk about that later. I just wanted to see if you guys knew that. Given the height of a ball thrown up at initial velocity of 5 meters per second, initial height of 2 meters, I'm giving you the height function. Find the max height of the ball. Max height of the ball. Let's forget the application part and just go straight calculus. You find a maximum by finding where its derivative goes positive to negative. So I want to know where h prime, or the velocity, goes positive to negative. Doesn't that make sense? That would mean it stopped going up and started going down if velocity was positive and negative. So I need to start by finding the velocity. What's the derivative of the height? Negative 9.8 meters per second per second. That's acceleration due to gravity. Plus 5 equals 0 at time equal 5 over 9.8, or negative 5 over negative 9.8, or 5 over 9.8. Do you agree? Okay, before that time, think small times, or negative times, or 0 time. Would this be positive or negative? Positive. And after that point, a large t would be a large negative, and so we'd get an overall negative. So did we get a max there? Yes. Yes, okay. So is the max height 5 over 9.8? No, silly, that's not answering the question. That's when the max height, not what the max height. The max height is height at whatever that is. In the interest of time, we'll just say 5 over 9.8 because v prime goes positive to negative. Not v prime, h prime, dum-dum. H prime goes positive to negative. We? Okay, last but not least, on the front page. Given the position of a runner in the table, estimate her velocity at time 3 seconds. This is Esther in this table, right here. I hope it's fast. Sorry, I hope if it's not fast, it's not. Can you do this for me? Okay. Do you have any way to take a derivative? Can you take a derivative without an equation on which to take a derivative? You cannot, okay? So the idea is that the best you can do to estimate dx dt is to say it's close to the average rate of change over the interval, as close to the moment you talk about as possible. So at time 3 seconds, I could actually use time 3 and time 4 and say how far did they go in that second after 3. You could also use time 2 and time 3 and talk about before, and that would be justified. You could even go 2 to 4 in a symmetric idea, but you definitely would never use 0 because the whole idea of a derivative is get as tight around that moment as you want, all right? So let's say we talked about the position at 4 minus the position at 3 over the time interval of 1 second. How far did this runner go in that time interval? 8 meters in 1 second. So it looks like at that point she's going 8 meters per second. Okay? Now it is crucial that you have an approximation. If you say equals on the AP test, you will lose a point. In fact, it's only a point and you lose that point, even if your number is correct. Okay? It's an approximation. Okay, now let's talk the other way. Instead of derivatives in calculus and motion, integration in calculus and motion. All right? Okay, a car is accelerating at 7e to the t meters per second at any time. The velocity of the car is 3 meters per second at time 0. Find an equation for the velocity at any time. All right, so let's start with the calculus relationship. How do I get velocity from acceleration? What do? You integrate it, okay? So velocity is the antiderivative of acceleration. The first thing you do is say, do I take the derivative or do I take the antiderivative? So I'm going to anti-differentiate 7e to the t. Now I don't really have a time frame in mind. They didn't say, go from time 1 to time 2 seconds. Then I might use limits of integration at definite interval. They just said find the velocity at any time. So I need to anti-differentiate an indefinite integral because I want the velocity at any time. So no limits. You with me? What is the antiderivative? 7e to the t plus c. Okay? If you are in the that's the BCC. Okay. If you said that's initial velocity, absolutely scratch that as garbage, not true. Please don't ever say that. It's not true. Okay. We use this initial condition or initial condition to find the c. The velocity is 3 when time is 0. Now when I put those two things in, that leaves me with just the c. And the c then is 4. Therefore, my velocity equation complete is 7e to the t minus 4. That's the velocity of the t. You follow? Okay. Let's try this bad boy, all right? So I'm giving you the velocity function, and I want the position function. So what's the position relationship to velocity? Is it the derivative or the antiderivative? Antiderivative. Start there, write it. Velocity is the antiderivative of position. We'll call it, you want to call it x or s? X. Okay? Oops, I just totally rearranged them. Sorry. Position is the antiderivative of velocity. So here I go. Root sine of t, cosine of t dt. How do I integrate that? U sub. Beautiful. U is sine of t. Du is cosine of t dt. Cosine t dt. I didn't need to do any tweaking. It's just straight up the square root of u du. Or think u to the 1/2. What's the power rule antiderivative of u to the 1/2? Raise it by 1. So 2/3 u to the 3/2 plus c. Do we sub back or not in this case? We do sub back in antiderivative cases, not in definite integral cases. So we have 2/3 of, what is u again? Sine of t plus c. That represents position. All right. Now then, we use the initial condition to find the c. We know that the position, or x, is 3 when time is 0. So if we use that in here, then x is 3. 2/3 of sine of 0 to the 3/2 plus c. What is sine of 0? 0. So it looks like c is 3. Therefore, x is 2/3 of sine to the 3/2 plus 3. You follow? Okay, you try that bad boy. Work with your math amigos. Notice it's 2 crosses. Did a velocity function like I did, or are you still working? Now, I was taught to, in such a problem, pre-reading, you're going to see 2 constants of integration. One when you go to get the velocity, and then another one when you get to the acceleration or to the position. Those are different, and that's why I use subscripts to label them different. C1 versus C2, they're not the same constant. You could also use CA or something along those lines. Definitely just don't use X, A, V, or T. Second one's a little messy, huh? Good thing you can add fractions in it, right? Now I feel dumb if I do something else. Actually, I'll go slower. The arithmetic imperative, maybe 6 minus 8 thirds. 62 is 6 minus 8 thirds, or C2 is 10 thirds. So, your position function should check all work. 1/3 t cubed plus 3/2 t squared minus 9t plus 10 thirds. Do you agree? All righty then. Okay, now let's talk definite integral here. This is a slightly different kind of problem in that if you were asked just to find an actual instant, you wouldn't necessarily have to get an antiderivative. Let me explain. Say I gave you this acceleration function which is really hideous and cannot be anti-differentiated by hand. There is no antiderivative. Okay? Oh, that's actually much longer than I thought. Wow, that's really gross. And if I gave you the velocity of 0 is 1, all right? Now this kind of goes to what we were talking about yesterday. Didn't we talk yesterday about how if you take the antiderivative of f prime from a to b by fundamental theorem, we could do that and then rearrange stuff if we wanted to, right? Now we're going to do that here, but in an application setting, not so much just generic, but applied. Now if I wanted to use the fundamental theorem to express what this is equivalent to in velocity terms and explain the meaning, that's actually a very common free response AP problem. Okay? They won't give you as much wording. They'll just say, they won't say fundamental theorem, they won't say velocity, they'll just say interpret this integral. Okay? Now by fundamental theorem of calculus, anytime you do a definite integral, don't you take the antiderivative and at the upper minus the lower. Now what's the antiderivative of acceleration? Velocity. At the upper minus at the lower. Now this, not clear at all what this means, but this, pretty clear. This represents this, and this is the change in the velocity from time 0 to time 5. Okay, so this represents the change in velocity. Now they actually look for 4 things. When they look for an integral interpretation, you should see 4 things. What it is with units, when it is with units. Right? Now I have what it is. It's the change in velocity with units. What units? If it's velocity, then it should be in, I didn't say. Did I say anywhere? Oh, sorry. Velocity is, let's call this feet per second. Okay? Velocity in feet per second from time equals 0 seconds to time equal 5 seconds. What it is with units, when it is with units. Right? Now, say we wanted to find out how fast it was going at time 5. I definitely don't want to do like I previously did and try and find the antiderivative, because that is a nightmare. Instead, I'm going to use more of a definite integral fundamental theorem approach, because I could have the calculator do the area under the curve, and I have a starting point. So with a little rearranging, I could work this out. So V at 5, if I take this and rearrange it, couldn't I move V initial over and say the velocity at 5 is the initial plus the integral? Now that actually makes a good deal of sense, because that's the initial velocity plus the change. Didn't we just say that that integral represents the change? So if we take the initial plus the change, that should give us the velocity later, right? All right, so that's where our calculator comes in. We're going to have our calculator do the heavy lifting for us. It's going to make a numerical estimate of the area under the curve. So we're going to type in something like 1 plus the integral value. This is worth practicing, I believe. I'm thinking about my time, but I do think it's worth it. I need to. There it is. Okay. So first plug in the initial v at 0 is 1, yeah? So 1 plus, how do I get a definite integral? Shift plus. Okay, from when to when? 0 to 5. 5 of. Now here's where entering it is tricky. Make sure you do it well. 7e to the sine. You can use t in the Inspire. In the 84, you have to use x. So if you use t, that's fine. 4 minus. I need to move this up, maybe. Okay, excuse me. 4 minus t times, what's the next part? Arc tangent of t over 12 times arctangent is inverse tangent, same thing. T divided by 12 divided by 12 dt now, obviously, because you're integrating with respect to t, or t is your variable of integration. I get 11.42305. How about you? Okay, so 11, that's an approximation because I'm rounding, 11.42305. Oops. And there we go. Okay, now, there are a lot of AP problems just like this. Often they involve a table first, but we'll talk about those. But my point is this: you're starting to get enough calculus to do a lot of free response problems when you can do these problems. So we can start doing some free response Fridays or warm-ups with free responses. By the time I am done with you, when you take the AP test, you will have done more than 70 free responses, and you will have seen a lot. Not everything, but a lot. Okay? I believe that's at the end of the notes, isn't it? It's not the end of the notes? These are like the most endless notes ever. What the heck? There's more. Should we do it? You want to try one on your own, or should we go over the homework? Fail? Tell you what, let's make this a problem on tonight's homework. Don't you want to practice this? No. It feels like you do, lady.
I feel like there's probably already a problem.
Let's replace number 23. Do this instead of 23.
Why? There is a 20. It's this big fat one.
Oh, I already have that?
Yeah.
Oh, no, I don't want to replace that.
So don't, just keep this.
All right. All right, you wore me down, you bunch of sissies. All right, whatever. Okay, darn learning. Questions on 50 something? 3? The BC students especially start saying, hey, could you start putting these online? It helps me a lot. I worry about Copy Fest, but I gotta be honest, I'll get you. I mean, if you're copying my key, I'll really stash it. So the keys will be online. At the very least, I'll work any problem that's roughly difficult. Although none of them really are difficult. So the key to 53 is online, or at least hints to how to do some problems. Questions on 53? 2. 2 must have been rough. Did you say 3? Yeah. Okay. 2, 3. Here maybe we need a front sheet on optimization. 13.
16.
14.
No, just kidding. No,
Not 14.
not
14.
No, I just got
14. 22.
Oh, 22 is one.
Okay, here we go. 2. Is 2 replaced or straight up out of the book? Straight up out of the book. Here we go. Okay. 2. Lori had a 6x6 square metal sheet, and she wants to make a box out of it. Whether you know it or not, this is actually the easiest type of this problem. If you have to put a lid on it, it's about 4 times as hard. Okay? Put a lid on it. It's an open top box. So you take a snip out of each. Okay? When you take a snip out of each, then you get this kind of shape that looks like this, if I tried to draw it in perspective. If you then fold along those lines, then it starts to fold up into a box, yeah? Okay, now what I want you to do is look at this green and trace back to where it came from. Now this was 6, but I don't know how much I'm taking out of each. So how long is that green segment if it was 6, and I took x off each side? It's 6 minus 2x. Okay? By the same token, this side relates to this side, which relates to 6 take away an x and an x. So it's also 6 minus 2x. And what's the height? That's the flap itself, and so that would be how big the square is. So the volume is length times width times height, 6 minus 2x, 6 minus 2x times x. We have 2 variables only, so no substitution necessary. That's cool. I want to know where V prime goes what for a max volume? Positive to negative. Now my next question is, all right, should I do a little algebra distributing, or do I really want to be brave and do a 3-part product? Algebra distribute, okay. Probably the wisest. 36 minus 12x minus 12x plus 4x squared times x, all said 4x cubed minus 24x squared plus 36x is a clean equation. You heard that? Okay. Anyway, V prime, are you on your way or should we continue? Continue, okay. Find the critical numbers. Let's take out a 12, shall we? Come on, this is soft. All right. This one, unlike, I think the one on last 2 nights ago's homework, it didn't factor. You had to do quadratic formula, right? This one does factor. The critical numbers are x equal to 3 and 1, yeah? Okay. If you were to talk about feasible domain here, though, I understand this is a cube, and it's got all these possible roots here. Actually, it's got roots of... So it's a volume equation, looks like that. But if you think about what's actually feasible for how big of a square you could cut out, if this is 6, what's the greatest x could be that you could cut out from both sides? 3. You could not cut out more than 3. So actually, the only real critical number of value where the max is 1. And so when volume, or when x equals 1, or when you cut little 1 inch by 1 inch squares out of the corners, that's when the volume would be its greatest. Last is to answer the question. There's a max at x equal 1. Question is, what size square do we cut out, or what's the greatest volume? Which question did they ask? They said, find the dimensions of the box with greatest volume, and what is the volume of the box? If x is 1, then what are the dimensions of the box? 4 by 4 by 1, and the max volume of that is 16, right? Okay, that's 2. 3. Is 3 still a question? Okay, now 3 is not an optimization problem, it's a related rates problem. So talk to me about givens. A square is being enlarged so that the sides increase at a rate of 2 centimeters per second. That means you're given dx dt is positive 2 centimeters per second, wait. And they want, how fast is the area increasing when the sides are 6, and how fast is the perimeter increasing? They want the ADT and the PDT when x equals 6. So what's the area of a square? X squared. What do I differentiate with respect to? dA dx or dA dt? dt. I want to change with time to x dx dt. Use the chain rule on the right hand side, the derivative of x squared, but then times the derivative of the variable with respect to time. The ADT at the instant when x equals 6 is something like 2 times 6 times 2, or 24. What are the units on the area change over time? Centimeters squared per second. Area per dA. All right. What about perimeter? What's the perimeter of a square? 4x, right? 4 sides all the same? So dp dx or dp dt. dt, changing with time, is 4. Dx dt, substituting in, doesn't actually matter the time. It's the perimeter is always changing at 4 times what a side changes. That makes sense, actually. 8 centimeters per second. The perimeter always changes at 4 times the rate of the side change. Okay, how about 13? 13 yet? You need 13 still? Okay. 13 is it replaced or used or close? Okay, it's a use sub problem. Use sub is definitely on the test. Yesterday you have a test Thursday. You have a test Thursday. Friday? Is Friday better?
Yeah.
You can say no. How many would prefer a test Friday?
Good morning, Dublin
Friday it
Jaguars.
is.
Please rise to the Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
A large pile of long set items brought to the clinic. Please come down and check for your missing items. The items we donated out.
All right, 13.
Northern Arizona University from Flagstaff, Arizona will be here during 7 hours a day. They offer tuition free, where all 4 years are lost costs, which means no increases, and they are part of the WUE program, an automatic grant for qualifying students. Want to know more about them? Sign up
Would
and
you prefer Wednesday? Sure.
Tomorrow, look for Kansas State University from Manhattan.
Ooh.
And Seattle University from Seattle, Washington.
the winner of My Favorite Book Library Drive is Kiara Nobler.
So
Kiara won the
this,
Amazon gift card worth $10. Congratulations,
it's
Kiara.
there.
Please
It's
come
just
down to the
there.
library to
I
claim your
didn't
prize.
do anything with it, so I guess it's there.
Congratulations to
So that one have to be brought up
qualified
front.
for the final round of UNC math competition this year.
And what is the
Emily Yang, Vincent Cushnie, Shane Miller, Samantha N., Helen Zhao, Drew Aparicio, Hayden Cushnie, Joshua McPeters, Isaac Lee, Amanda Geit, Jack Kowalski, and Emma Rickman. See your math teacher for information about the live.
Senior high students, there will be a girls' soccer meeting this Thursday at 2:30 in the cafeteria for all athletes interested in playing.
You agree? So the one half push it out front, and it actually goes way later.
Last names are
Cool.
key. Will be required to calculate for
Send
7
this stuff
hours.
out.
Please report.
Are we good on 13? 42.
Last name E to MA will be required. That's all your announcements. Have a great day.
You said no teams.
But I told John.
Oh, sorry.
I just need to know.
Two is, oh yeah, 16 is a home game. Okay. 16, you definitely want to use. Okay, so what did you think actually? Let's go. U is So this is a function within a function. So u should be sine squared. So du, here's where you need to be on your game. What's the derivative of sine squared? 2 sine times the derivative of the inside, cosine. Now that actually by identity is, that is sine of 2x. So this becomes cosine of u du. That's then done. Okay? I'll put 22 up on my website. Have a lovely day. Sine u plus c, so I'm feeling sine of sine squared plus c. No. Because the antiderivative of cosine is negative. Derivative. Okay. Have a lovely day. You're welcome.